Show of hands, how many people understand this program? Yeah. Our cameraman understands. So, what does this do? What does this line do? Hashtag. What's it? Yeah.
Preprocessor directives include this file.
Yeah. So this is actually not it's kind of not part of C++. So remember how I said there's a lot of things under the hood with G++? The first step that runs is what's called the preprocessor step. So this actually runs before the compiler. So anything with a hashtag is actually not part of C++. It's actually part of the C preprocessor. It comes from the C language, and it itself is not really part of the C language. It runs before the compiler. And there's a lot of fancy schmancy stuff you can do with these preprocessor directives. It's the only way of doing things like reflection, or like, could you make a program that, for example, prints out all of the member variables of the class? Think about that. Kind of useful, isn't it?
Yeah.
Like if you want to do documentation, right? Write a program in C++ that, given a class, prints out all of the member variables and all the functions. That'd be neat, right? Can't do it. No way to do it. Yeah. They're talking about adding reflection. Reflection is the ability to get a list of that kind of stuff. They're talking about adding it in C++ 23. It's not going to. C++ 23 is next year. Probably 26, maybe. We'll see. Can't do it, but you can do it using preprocessor drivers. So if you guys have ever taken my game development class, you can use Unreal Engine. Unreal Engine has the ability to interface between C++ and the Unreal Engine. And in order to do that, it needs to know what kind of functions you have and what kind of variables you have. And so they use the preprocessor directive to sort of tag things, and it generates a list. And that list gets exported into, it's all under the hood kind of stuff, but basically the upshot is that the game engine knows which variables you have, which functions you have, and it will appear inside of the engine. That's really cool. Okay. So preprocessor runs first, and if you want, there's a compiler flag you can do that will show you the output of this after the preprocessor step runs. I never do that, so I'd have to look it up off the top of my head. What is it, like G++-I? Yeah, I don't remember what Somebody look that up for me. Get the preprocessor output. I basically don't do it except in this class, just as a demonstration.
Dash E.
Dash E?
Capital E.
Dash capital E, thank you. Oh, maybe it says it now. Okay. So, write this into main.i. So this is what Hello World looks like, actually. All this stuff here comes from hashtag include IO stream. My Hello World program is now 44,000 lines. Right? Like, that's a bit excessive, isn't it? I'm sure I don't even need all those lines, But this is all stuff that was just copy pasted in from hashtag include IO stream. That's it. I deleted the other stuff, right? Didn't I? Yeah, I deleted the other. So all that stuff is just from hashtag include IO stream. Question?
Oh no.
Yeah. See, Anytime the student's hand goes above the shoulder, it's like a Pavlovian response from a professor. Oh, question. So this little thing here turned into a 44,000 line monstrosity. We're 6,000 lines in right now.
Oh boy.
This is hello world. This is hello world actually. This is what the compiler sees. The compiler actually doesn't see this because the preprocessor runs first. You guys understand? What the compiler actually gets is this. At the very, very bottom, there it is. That's at the very bottom.
Wow.
Hello. Yeah. Yeah. This is changing. So C++ 20 added an alternative to doing include files called modules. But they're still not ready for prime time yet, so sometime soon, maybe by the end of the semester, who knows? We can talk about modules, but for now it's still preprocessor. Then the compiler. Okay? So the compiler doesn't generate a.out. We think it does. But the only reason why we think that is because it just erases this afterwards. Okay? There's actually another step in there, and erases that step too. The assembler actually generates the .o file. So the assembler generates a .o file, and then there's something called the linker. That's the linker there. The linker turns it into an executable. There's all these steps, and they all just get hidden. Because why? When you're welcome to CSCI 40, here's hello world, compile it, run it, right? The whole point is to make the first day experience in computer science simple as possible, right? Not anymore, it's CSCI 45. You guys gotta learn the actual truth, what's going on, yeah.
Did we learn anything about the object file?
Yeah, let's learn right now, why not? Let's do it, yeah.
Can we do a hello world in assembly?
Yeah, absolutely.
Sounds fun.
It's surprisingly complicated.
Oh
It's
boy.
surprisingly complicated. It's actually probably week 6 or something like that to get to
Oh my
hello world.
gosh, really?
Yeah. Yeah, hello world is not easy in assembly.
Oh boy.
It's 44,000 lines!
But can you get down to like 20?
We'll see. We'll see. Okay. So let's not do hello world anymore. Let's make it simple. Let's get rid of that. Let's get rid of that. Let's make the simplest C++ program in existence. There it is.
Let's see.
That's a valid C++ program. You don't know what it does? What does it do?
Return 0.
Return 0. Okay. So what was it? G++-E, main.cc, and there is our program. So it adds a little bit of notes. The preprocessor writes down what file we're in, what directory we're in. What's that?
From 44,000 lines to 8 lines?
Yeah, because we took out hello world. Yeah, there you go. So that's step 1. You guys see that? Step 1. You guys ready for step 2? He's not ready. All right, switch off with him, somebody. Who wants to be the video person? I know you don't want to miss this. You're gonna get to see assembly for the first time. Anyone? All right. Thank you, sir.
Sorry, you're
All
recording.
right. Still recording? All right, cool. Awesome. You got it. All right, let's do this. Let's see some assembly. So we just did this step, right? We just did the preprocessor step. -S is the assembly step. Okay. So that just generated a file called main.s. S is the name of an assembly file. Why is it not called .a? Why is it S? Why is it not called a .as file? That's the real question. Could be. .s. You don't know? .a is used already for archive files. So an archive file is .a. So an assembly file is .s. And it's -S to compile using an assembler. And that is assembly. What does that mean? I have no idea.
That's a long word.
This is assembly.
Oh dear Lord.
What the hell is happening? happening here? This is our program. Right? Like, what the hell is going on? It's 3,000 lines of code. What the hell is happening? Maybe let's turn the assembler on. Let's turn the optimizer on. Let's turn the optimizer on. This will help, right? Whoa, what happened here? Den. No, not den. Not den. Not den. I'm sorry. Sorry, den. Don't hurt me. Okay. Let's try this now. Den main.s and 155 lines. There you go. All of this stuff here is pointless. This is all pointless debugging stuff. Like it's telling us the file that we came from was main.cc. .text means we're now entering the coding section. This is all just boilerplate. It's all boilerplate. None of it means anything useful. Here's
Literally just those brackets.
yeah. Where is the actual? Here's main. Okay, align, long, screen, align. Somewhere in here, there's going to be a line that says somewhere. I'm not going to bother finding it. Okay. So let's run it. G++-03. Let's optimize the hell out of this. This will be the fastest execution time ever. Let's do this. Time, 8.0. 0 seconds. Look at that. This is Back to the Future level speed. 0 seconds. 0 CPU time. It's that fast. Okay? And so what happened? We returned 0 to the operating system. If you are curious about that, you can return 42 if you like. The return value out of main is the error code of your program. Okay? So if you were to compile this, let's make sure the optimizer's on. We don't want to waste our time. If you echo the error code, you can echo the error code with that little bit of magic there. $? Is the error code returned by a program. Let's see, you return 42. Okay. What is the error code used for? Well, you know? Yeah.
Take crack at 0.
0 means, 0 is the normal error code. 0 means no error code. And that's why usually most programs you see at the bottom of main will say return 0. It's no error code. But what is it used for? Yeah.
I was going to ask a separate question, but return 0 just means like nothing bad happened.
It means nothing bad happened. But what is it used for? Who uses that? Who cares about the error code? Who does it get returned to?
The program.
The operating system. Yeah. So it passes the error. So Unix, in this case, we're using a Linux system. The operating system runs the program, and then after the program finishes, the operating system is delivered an error code. And we can report what that error code is using that. But what does Unix do with it by default? Absolutely nothing. You return 42, it's like, all right, cool, bro. Doesn't do it. It's there if you need it. And why? Why? Well, here's my compile program that I made for you guys. And what happens is I run a static checker on your thing, and if the error code was returned to be 1, it quits. If it succeeded, then it moves on to the next step. And if that one had an error, it quits. If that one succeeded, it moves on to the next one. If that one had an error, it quits. So error codes are useful in like shell scripting and things like that. Like if you want to script if you want to write a script that will run one program, and then if that one succeeded, run another program. If that one succeeded, run another one. You guys understand? At least that makes sense. Okay. But if an error occurs, just stop. So that's what these kinds of things are used for. Why does it matter for us? Because hello world is hard. So when you write your first assembly program, you're actually going to be returning a value here. Because actually outputting things to the screen is actually difficult in assembly. Okay. So step 3, assembler. Step 4, linker. So the next step in this process is this. So the assembler generates a .o file. A .o file is when you're starting to get into something that looks like something the CPU will actually understand. Okay? Even assembly is human readable. Assembly is human readable. You might not believe me after seeing that mess that it threw up on the screen there, but it is human readable. You guys will be reading assembly and understanding that kind of stuff by the end of the semester. Not an .o file is not human readable, unless you're like a super sane computer science major. If you guys want to look at the .o file, vim it, why not? Let's do this. That's what it looks like. Okay. So there's parts of it that you can see there's like strings embedded in there somewhere. You know, most of it is just garbage, right? So you need to use tools to actually understand a .o file. There's tools like object dump, which dumps an object file. There's nm that shows you the names that are inside of it. Once you get into a .o file, you need tools to actually understand it. You can't just like vim it anymore, right? And so this is the .o file. That's the whole thing right there. Okay. So it is moving 2A into EAX and returning. What is 2A? We all know what 2B is or not. What is 2A? It's 0 times 2A. Isn't 0 times 2A 0? That's odd.
Is that the memory address?
Good guess. Memory address is on the left. So the left there is the memory address 0. And then 4 words later, we're here. 4 words later, 5 words later, we're here. Yep. That's the memory address on the left. This is the actual bytes of the file. And then this is the disassembly. So it's saying, if you ever see in a file F3OF1EFA, that means whatever the hell that is in assembly. B8 B8 means move 2A 00 is EAX. The hell is EAX? What the hell? Welcome to assembly class. This is x86.
So are those the names of the registries on it then?
Yeah, let me explain. So EAX is a register. And I'll explain what a register is in a second. Right now I was asking you, what is 0 times 2A? 0. No, this is hexadecimal. So hexadecimal is base 16 numbers, and we're going to be having a whole lecture on hex. But basically, it's called hex. Hex also means a curse. You might be feeling that right now. Looking at this feels like a curse, perhaps. But no, this is base 16 numbers. So what is 2 times 16?
32.
32. And A, in hexadecimal, you count like this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. 16 is F, A is 10. Good. 2 times 16 is what?
32.
Plus 10?
42.
You guys remember what number we were returning?
42.
42. So this is saying put 42 into EAX. EAX is the return value register in assembly for x86. Okay. And so what the hell is a register? Inside of a CPU, there are these things called registers. This is a crucial, fundamental core concept for this class. So if you guys are about to fall asleep, now's not the time. Inside of x86, there's only a handful of registers. There's EAX, EBX, etc. In ARM, there's 16. There's 16 registers in ARM 32. What the hell is a register? A register is a variable in hardware. Okay? It's a variable. So in C++, if you say x is equal to 7, somewhere deep within the assembly file, it'll say put the number 7 into that register right there. It is the hardware equivalent of a variable. And if you say z is equal to x plus y, x is going to be some register, y is going to be some register, z is going to be some register. The assembly code will say add the value in that register, add the value in that register, store it in that register. That's assembly programming at its heart. It works on registers. You have values in registers, you add them, you subtract them, you multiply them, you divide them, except not on ARM. ARM doesn't have division. What? Yep. ARM32 has no division, has no modulus. Just add, subtract, and multiply. It's a simpler x86 after. ARM doesn't. Yep. What's that?
So you can make it, right?
You make it, yeah. Yeah, you have to write assembly code, yeah. Yeah, so what this is doing, it's saying put the value of 42 into that register, and then it returns. That means return. That's it. EAX is the register that return values are. So when the operating system comes back, it checks what's in EAX. It's like, okay, that's the return value. And if you ever ask it, hey, what was the return value? Echo, whatever. It grabs the value from that register and prints it as a string. Are you guys with me? So that's a .o file. And then finally, at the end of this long journey, we're gonna get to an executable. Can we run a .o file? No. It needs to be turned into an executable. And that's the job of the linker. Another thing that probably most of you have never heard of before. All these unsung heroes that are just all hidden, Most of the time, they're just hidden right here. They're all under that umbrella. You type G++ hello world, it makes an A.app, you run it, cool, it runs. You didn't know there was 44,000 lines of code, that there was all that garbage assembly, this thing called a linker runs, all that's a hidden heroes, right? So, what does the linker do? The linker makes executable. No, there you go. Nope, sorry. LD. There we go. And chmod, everybody may execute. Get that out. You run it, and it crashes. Cool. That's exactly what I wanted to see. Okay. So the reason why it crashed is because I don't remember the command line parameters that I need to pass to LD, because I never run it by hand. Why? Because I use G++. But in fact, you can do that. You guys see that? Or I can do this. Right. Or I can do this. Oh, let's run the program first. That makes a little more sense, right? The point being is that G++ is pretty cool. If you pass it a source code, do you guys see